Welcome to the second module. In the previous module, we had seen how we do a differentiation of basic power of x to the power n. And then we had talked about the derivatives of the sum of two functions, difference of two functions, product of two functions, and the quotient of two functions. Now let us continue and see what is the application of these derivatives. Now in this slide, we see a graph of a function y is equal to f of x. Now here you see the nature of the curve. It is increasing. At point A, there is a maximum. Then the value of y starts decreasing. At B, we have a minimum, and again it's increasing. So we call these points as local maximum and local minimum. Observe that at each of these points, when I draw the tangent at A, this tangent is parallel to the x-axis. Similarly, when we draw the tangent at B, this is also parallel to the x-axis. We call them as local maximum and local minimum because there may be another point beyond this point where the function may be still higher or maybe little lower. So we talk about the maximum as a local in this neighborhood. These 2 points A and B, where your tangent is parallel to the x-axis or where the slope of the tangent is 0, are called as the stationary points of the function. So stationary points are the points at which we can say the slope of the tangent is 0, or we can also say that dy by dx vanishes. So how do we find these stationary points in a curve? So as we had seen, stationary points are the points on a curve where the derivative of fx is 0. That is, f prime x is 0. So here look at this point, x equal to minus 2. This is the maximum point, and we have to check whether here the derivative is 0. Similarly, we should check here at x equal to 1, where it's a minimum point, whether the derivative is 0. So these are the points of local maxima or minima. So let us see how we will find this. So the graph is of the following function. This graph that we are seeing here, fx here represents, fx is 2x cube plus 3x square minus 12x minus 5. Now we can find out f prime x. So we will get 6x square plus 6x minus 12. I am sure by now you all are settled to check this out. Now what we do, as I said, at the point where you have the tangent parallel to the x-axis, f prime x is 0. So we equate this to 0. So we put 6x square plus 6x minus 12 equal to 0. 6 is common. We can remove it. We get the quadratic equation as x square plus x minus 2 is 0. Now this is your simple 8th standard maths. We can factorize it. And we would get x plus 2 into x minus 1 is equal to 0. Now the product of two terms is 0. So one of them is definitely 0. So either x plus 2 is 0, which gives me x is equal to minus 2, or x minus 1 is 0, which gives me x equal to 1. So these 2 points are the points. What does it mean? These are the points at which f prime x becomes 0 for these values of x. And they are called as the stationary points in the curve. So now we plot this on this graph. See, we can verify it. So let us look at the value of the function at x equal to minus 2. That will give me the y point here. Y is f of x. So when I put x equal to minus 2 in fx, recall fx is 2x cube plus 3x square minus 12x minus 5. And we are substituting x equal to minus 2 here. So we will get 2 into minus 2 cube plus 3 into minus 2 square minus 12 into minus 2 minus 5, which we can simplify and we get 15. Likewise, at x equal to 1, f of 1 is 2 into 1 cube plus 3 into 1 square minus 12 into 1 minus 5, which gives me a minus 12. So now for x equal to minus 2, f of minus 2 is 15. So I can mark this point. You can see it here. For x equal to minus 2, I have marked fx is y is 15. Likewise, for x equal to 1, we have marked y is minus 12. Now we'll bring back the curve on this picture. So here, this was the plot we started with, and we observed that these 2 points, x equal to minus 2 and x equal to 1, are indeed the values of x for which fx is a maximum and fx is a minimum here. So how did we find these stationary points? We took the function, we took its first derivative, we equated it to 0. Then, based on that equation, the values of x which we get are called as the stationary points or the points of local maximum and local minimum. Now let us understand what is the behavior of the tangent here or the gradient. So what happens, look at the left of A. If I keep drawing the tangent at every point, you see that it is increasing. The values are increasing here. So the rate of change of y with respect to x is increasing. Now at this point, the tangent is 0. It becomes parallel to the x-axis. So dy by dx becomes 0 here. Now y is decreasing as x increases. So what is the behavior of dy by dx? It becomes negative. So here y is increasing as x increases. So dy by dx is positive. Then it becomes 0. Then dy by dx becomes negative. So understand, if A is a point of local maximum at A, which we are calling a local maximum, the gradient or dy by dx, do not worry about the term gradient. You understand gradient is nothing but dy by dx. So dy by dx changes from positive to 0 and then it becomes negative. So it is from increasing to decreasing. Okay. Now likewise, if we analyze the behavior near the point B, now here you see dy by dx was negative. Y was decreasing as x was increasing. Then once again y became 0, and after the point B now y is increasing as x is increasing. So at a point of local minimum, which is indicated by B, the gradient changes from negative to 0 to positive. So the gradient is therefore increasing. It is first decreasing and after the minimum it starts increasing. So observe here that at both the points A and B, there is a change in the behavior of dy by dx. At A, which is a maximum, it is increasing and then it is decreasing. And then at B, dy by dx is first negative and then it becomes positive. So we had used the test that dy by dx is 0 to find out whether it's a local maximum or local minimum. But that doesn't tell us whether the point is a maximum or a minimum. It only tells us that the slope vanishes here. So dy by dx is 0 at A as well as at B. Now we make use of this behavior of dy by dx, that when it is a maximum, dy by dx is increasing first and then it decreases. In that case, it's a maximum. Similarly, the rate of change of dy by dx is negative first and then it increases. So that is a minimum. So to identify whether a given stationary point, both of them are stationary points, but now we have to understand whether the stationary point is a maximum or it is a minimum. To understand that, we make use of the second derivative. So the first derivative only tells us that it can be a maximum or a minimum. Now, when the derivative is positive first, it is increasing, and when it is negative, it is decreasing. So when we take the second derivative, it represents us the rate of change of the gradient. So we are actually taking the derivative of the gradient. So now here you see we are making use of the second order derivative. We are talking about d by dx of dy by dx. How is dy by dx changing? So when it is changing from positive to negative, we say that the rate of change is d2y by dx square is less than 0, this case. And when the derivative of dy by dx is changing from negative to positive, the rate of change of dy by dx is greater than 0. So, as in the previous slide we had seen, we didn't see the behavior of y with respect to x. This plus minus sign indicate the behavior of dy by dx with respect to x. So we are talking about dy by dx is increasing and then it is decreasing. So the second derivative of y is negative here. So that indicates a maximum. So how do we test whether a stationary point is a maximum or a minimum? So first of all, we use dy by dx equal to 0 to find the stationary points, just as we had found x equal to -2 and x equal to 1 by substituting f prime of x equal to 0. Now to check whether x equal to -2 is a maximum or a minimum, we find the second derivative. So we find the second derivative at the point x equal to -2. Now if the second derivative is less than 0, the point AB is a local maximum. And if the second derivative at AB, so this is evaluated at the particular point, that is x equal to 1, it is greater than 0, then we say that the point is a local minimum. So we'll go and check out in the same function. We were given y is 2x cubed minus 9x squared plus 12x minus 3. So this is the function. We have to find the stationary points of this function and we have to determine the nature of the stationary points. What do I mean by the nature? Whether these stationary points represent a maxima or a minima. So we start with considering y is 2x cubed minus 9x squared plus 12x minus 3. Find out dy by dx, that is your first derivative. We will get 6x squared. Now 9 2s are 18x plus 12. Now to find the stationary points first, we have to equate this first derivative to 0. So the stationary points are found by solving dy by dx is equal to 0. So put this here, we can take out a 6 common and we will have x square minus 3x plus 4 is equal to 0. So let us find the solution of this equation here. So we have x square minus 3x plus 2 is equal to 0. When we collect a 6 common, this becomes. And now this is, you know how to factorize a quadratic equation. The middle term can be split as x square minus x minus 2x plus 2 is 0. And we will get the factors as x minus 1 into x minus 2 is equal to 0. So two factors we get. One is x minus 1. Here we need to write one more step. The other factor is x minus 2. Now when we equate each of the factors to 0, we get the stationary points as x is equal to 1 and x is equal to 2. So we have found for what values of x, f prime x is 0, to find the corresponding value of y. Just as in this slide, we had marked the point at which we get. So we had found what is y corresponding to that value of x. We can work it out from the expression for y. So what we do, we take x is equal to 1 and we put it here in y. So when we do that, we will get 2 minus 9 plus 12 minus 3. So we will get minus 9 minus 3 and plus 12 will get cancelled. We will get y is equal to 2. So x is equal to 1 and y is equal to 2 is one stationary point. Similarly, when we put x equal to 2 here, we can find that y is equal to 1. So now we have two stationary points on the curve. Whatever is this given function fx, it has two stationary points. X is 1, y is 2 and x is 2 and y is 1. Now we need to check whether these points are a maxima or a minima. So what we need to do, we need to go and apply the second derivative test. So we will have to use the second derivative and evaluate this derivative at the point x is 2, y is 1. So what do I mean by saying that I have to evaluate this d2y by dx square at x is 2, y is 1? You put that value here. So we put x equal to 2 here. There is no y. So we'll just put x equal to 2. We'll get 24 minus 18. So that is 6. So d2y by dx square at x equal to 2, the second case. So d2y by dx square when x is equal to 2 is 12 into 2 minus 18. We get it as 6. Now this is greater than 0. So that means it's a positive value. And what does my test say? When d2y by dx square is greater than 0, the point x equal to 2 is a local minimum. So here d2y by dx square is greater than 0. So this point x equal to 2, y is equal to 1 is a local minimum. Likewise, now we will test the other point x equal to 1. when you have x equal to 1, d2y by dx square is 12 into 1 minus 18. We get a minus 6. And this is less than 0. So this point 1, 2 is a local maximum. So we can make use of the concept of derivatives. The first derivative helps us to find what are the stationary points on the curve. And the second derivative helps us to identify whether that stationary point is a local maximum or local minimum. Now this concept of maxima minima is useful in several applications in physics, in maths, in machine learning. Wherever we talk of any maximization or minimization of a function, we use this concept of derivatives. Now let us look the same example with the help of a plot. So here this is the graph of the function 2x cubed minus 9x squared plus 12x minus 3. And clearly on this graph now when we plot it, we can see that x equal to 1 is a maximum and x equal to 2 is a minimum. The results which we had obtained just by differentiation even without seeing the plot. Okay, so x equal to 1 is a maximum and you see that it is a maximum here and x equal to 2 is a minimum. Yeah, so here is an exercise for all of you which you should try out to find out the second and higher order derivatives. Till now we have only found the second order derivative and we have used it to identify what is a maxima and what is a minima. Now for these two examples, you work out the first derivative, second derivative and third derivative. So you will also find d3y by dx cube. So here also you will find dy by dx, d2y by dx square and d3y by dx cube. All these formulas are given in our list of formulas. Having done that, you will use the previous whatever we have discussed to find the stationary points of these four functions. So these are the problems given to you to practice how to find the maxima and minima for a given function fx. Now we have discussed so much about functions of single variable. Where in real life do we encounter such things? So lot of applications, if you look at the variation of temperature with time. So T is a function of time. If we record the temperature in a location at different intervals of time, say every minute, then for every time interval we have a temperature. So we can write T is f of time or T is f of, I denote it as seconds, the time, f of s. Distance traveled by a car can be represented as a function of time. So D is f of t. Height of a plane, an aeroplane which is flying, we can express it as a function of time. So h is f of t. Grade of a student, you can talk it depends on the marks. So more the marks, better the grade. So we can write g is a function of m. So the concept of functions can be seen in several applications in real life. And then we can use, if you are interested in what is the maximum height a plane would achieve, then you can use this concept of maxima and minima and you can find out what is the maximum height achieved by a function during an interval of time. So we can find points of local maximum and local minimum in all these applications. Now we move to the concept of functions of two variables. So for a function of single variable, we have understood what is the concept of derivative, what are the stationary points, and what do we mean by maxima and minima, and how is the tangent at a point of a curve related to the derivative. So this is important that dy by dx at a particular point, if I evaluate, so say dy by dx at x equal to a is nothing but the slope of the tangent at x equal to a. Now all these concepts, we will extend it to a function of two variables. So once again, let us look at scenarios. Where do we get this functions of two variables? So now previously we were talking of variation of temperature with time. But now temperature may be different at different locations or in different cities. Say in Delhi, we have a different temperature at different times. In Bangalore, we have different temperatures at different times. So we can talk of temperature as a function of time and location. So now we have two variables. So we can write f is s of s comma location. Similarly, if you consider the profit of a company, it can depend on the number of units sold. And it can also depend on the money spent in advertising. The more you advertise, probably your profit is more. Similarly, more the number of units sold, the profit is more. So we can write profit as a function of number of units sold and the money spent in advertising. Now the grade of a student can be also written as a function of marks in maths and marks in physics. So we can write G is F of M comma P. So M denotes the marks in maths and P denotes the marks in physics. So these are some of the examples. There can be many where you have functions in two variables. So then what is multivariate calculus? Multivariate implies that there are multiple variables. So we are talking of one variable, two variable. Now you can have a function of 3 variables, 4 variables. So when we have multiple variables, we call it as multivariate calculus. So multivariate calculus is the field of calculus which involves multiple variables. So we started with a function z, which is a function of x. So here z is the dependent variable and you have one input variable x. So z is written as x square plus 4. Now your output is your function z. If this output depends on more than one input. So here z is depending only on x. Now suppose we have two variables x and y. Then you can declare z as a function of x comma y. So as a specific case, I can write here, I was writing z is x square plus 4. Let me write here z is x square plus y square. So what do you mean by function? When you give every value for x and y, say x is 1, y is 1, z will be 1. X is 2, y is 1, z will be 5. So 2 square plus 1 square will get a 5. So for every value of x and y now corresponding to a pair of values, we will have a unique value of z. Okay. So whereas in case of function of single variable, I was just giving a value of x. So when x is 1, y is 5. When x is 2, y is 8. Z is 8, sorry. X is 1, z is 5. X is 2, z is 8. But in case of function of two variables, just prescribing the x value is not enough. We have to give a value of x and we have to give a value of y. So the variables x and y are the inputs to the function and therefore they influence your output. Now if we try to plot this function z is equal to x square plus y square. So we had taken the plots of a single variable y is f of x and we had seen that it's a curve. Let me go back to that slide and just relate it. So this is a function. When it is a function of a single variable x, as we change x for different values of x, we write the values of y and join all these points. So the graph is a curve. It can be a line or it can be a parabola or any other curve. Now when we talk of plotting a function of two variables, x and y, we have to give, as I said, a value for x and a value for y. So suppose I say x is 1, y is 1, z is 2. So this will be marked as a height on this, a vertical height. So this is say my x-axis and this is my y-axis. So when x is 1 and y is 1, somewhere here, I mark the point on the top, which is z is 1. When I take x is 2, y is 2, I will get a point z is equal to 8, which I will mark somewhere here. So the z represents a vertical height on the graph and on the plane we have a set of values of x and y. So this is a square on which at one end all the values of x change from -5 to 5 and here y changes from -5 to 5 and corresponding to every value of xy I have a point z. So this curve is like a surface in the three-dimensional plane and this is how it looks. Okay, so just to make you visualize how you would see a function of two variables, a function of two variables is plotted on a three-dimensional plane where corresponding to every pair of values of x and y, we have a corresponding value of z. So these are few more examples where we have the function f of xy, x square sine y plotted. So here also the same thing. For every pair of x and y, we mark x square sine y on the top. Here also for every value of x and y, we evaluate the value sine ex cos log y and we put it here. So a function of two variables means, understand from this picture, you have a set of values of x and y and whatever is the function, you evaluate it and you get a z. Now that we have understood what is meant by function of two variables, let us see how do we find the derivative for such a function. Recall f prime x represents the rate of change of fx as x changes. So whenever x changes, the derivative f prime x tells you what will be the change in y. To extend this idea to a function of two independent variables, now here x and y are two independent variables, we have to understand what is meant by changing x and what is meant by changing y. So what we do to map it to the understanding of changing of one variable, we can hold y fixed. So we do not change y and we allow x to vary. When we do this, whatever we get like the f prime x, we call it as the partial derivative of f with respect to x. Why the word partial? Because this represents only the change in f with respect to x. We do not consider the change in f with respect to y. When we hold the x variable fixed and we allow y to vary, we call it as the partial derivative of f with respect to y. So we are now looking at keeping x fixed whenever we change y, how f changes. So this is similar to our concept of a function of a single variable because we are not seeing the effect of the second variable. So when we fix y, we are seeing the effect of only x. So we call it as the change with respect to x. When we fix x, we are looking at the change with respect to y. So we call it as the partial derivative of f with respect to y. Now let fxy be a function of two variables. So we have taken this. So this fx which I said, we denote it like this. F with respect to x, we write it as delta f by del x. So this we call as the partial derivative of f with respect to x, which is nothing but limit h tending to 0. Now see here I am keeping y as constant. So I am only writing x plus h minus fx into y, fxy. So y is not changed. We have changed x by a small amount, x plus h, and we are taking the difference. So the definition of the partial derivative is same like the definition of first order derivative, f of x plus h minus fx by h, limit h tending to 0. Only thing we have retained writing the y here and we have not allowed y to change. Likewise, when we write the partial derivative with respect to y, we will write it as limit h tending to 0. Now we will keep the x fixed. So y is changed by a quantity h, y plus h, and we have f of x comma y plus h minus f of x comma y over h. So limit h tending to 0. This is the rate of change of f with respect to y. And now as we are talking about the partial derivative, we don't write it as df by dx. We represent it as del f by del x. So this is the notation for partial derivative. We call it as del f by del x or f of x, and we write it as del f by del y or f of y. So let us see how we find out these partial derivatives with respect to x and y. Take the example fxy is x square plus y cube. Now, as I said, when we find the derivative del f by del x, we are going to treat y as a constant, and we know that the derivative of a constant is 0. We are talking about the derivative of sum of two functions. So this will be del by del x of x square plus del by del x of y cube. Now, when we do the differential of x square with respect to x, we get 2x. And since y is treated as a constant, we get this 0. So the partial derivative of f with respect to x is just 2x. Likewise, we can find the partial derivative of f with respect to y. So we have now del f by del y is del by del y of x square plus del by del y of y cube. Now in this case, when we are taking the partial derivative with respect to y, we need to treat x as a constant. So we take x square becomes a constant, so its derivative with respect to y is 0, and the partial derivative of y cube becomes 3y square. So when we have a function of two variables, we talk about the change with respect to x, and that is your del f by del x, and the change with respect to y, we denote it as del f by del y. So now let us understand what is meant by a graphical, how do you represent these partial derivatives on a graph. For a dy by dx, when it was a function of single variable, it was a tangent to a curve at a particular point AB. So now what do you mean by del f by del x at a particular point AB, the partial derivative of f with respect to x at a comma b? Now when I talk of the partial derivative of fxy with respect to x at a point AB, immediately it comes to my mind that b is going to be kept as a constant. We will not talk about the change in b. So fxy becomes equal to another function gx, where gx is fx comma b. So y is not changing, only x is changing. So look at this green line. I have fixed the value of y on this line to some value b. So now I am, instead of a surface, now I am on a curve, a single green line curve, and this is the graph of f of x comma b. Now, so it has been reduced to our case of a function of a single variable. And now if you come to the point AB, the derivative of gx, or if I say the derivative of f of a comma b, is nothing but g prime a. So it is the derivative of gx at the point x equal to a. So when we talk of function of two variables, the partial derivative is nothing but just like your ordinary derivative with one variable fixed. So this line is nothing but, it represents the slope of the tangent at this point a comma b. So already we had fixed y is equal to b, and now when you take g prime of a, we have also fixed x equal to a. So it represents the slope of the tangent at the point a comma b. Just like that we had seen for the ordinary derivative. So even in case of functions of several variables, the geometric perspective of derivative is, it is the slope of the tangent at that point. Now we can also find higher order derivatives of partial derivatives. So just as we had found dy by dx, d2y by dx square, we can find higher derivatives here also. So when I denote fx of x, it means I am taking the derivative of fx again with respect to x, and we denote it as fxx. So it means del by del x of del f by del x. Again we denote it as d2f del 2f by del x square. Similarly, I can differentiate the partial derivative of del f by del x with respect to y now. So that is del by del y of del f by del x. We write it as del 2f by del y del x. Del f by del y again differentiated with respect to x becomes del by del x of del f by del y. So it is del 2f by del x del y. And note here, these two may not be the same. So when you work out problems, you can observe that the derivative of del f by del x with respect to y need not be equal to the derivative of del f by del y with respect to x. And then we have the second order derivative fyy, which is del 2f by del y square. Now this is only for your information. You may not have to go and evaluate problems so much when you do machine learning. So this slide is just for your information. If you at some time you need, you can understand what is meant by higher order derivatives. So here we have evaluated using that formula fxy is x square y. So fxx, if we see, we are first differentiating with respect to, first we will find out the first order derivative. So it is, you are keeping y as a constant. So this is 2xy. Here I am treating x as a constant. So when I find out fy, so it is the derivative of y. So this part you have to understand a bit carefully. So when I do the derivative with respect to y, it will become del f by del y will become 1, and x square is treated as a constant. So this particular slide, spend some time and try to understand how it is worked out. And now when I am differentiating fx again with respect to x, now y is treated as a constant. So the differential of x is 1. So I will get a 2y. And fxy is now, I am differentiating this with respect to y. So when I am differentiating with this with respect to y, it will become 1. So fxy is 2x. Likewise, fyx means I am differentiating fy with respect to x. So it will be just 2x. Yeah, sorry, I think fxy will always come out equal to fyx. So these two values are same. And then when we do fyy, there is no term in y here, and x has been treated as a constant when we differentiate with respect to y. So x is a constant, therefore fyy will become 0. So here there is one more example which you can work out and see. And there is one exercise also given. Find the second order derivatives of all this. So this is a little difficult problem, but if you go and browse all the previous slides, it is an application of everything. You have the formula for cos 2x. Here we have the function of function. You have the product of two functions. So all these you have to make use of the concepts on the previous slide and find the second order derivative here. So work it out. Now we have been talking about the change of fxy, which is a function of two variables, with respect to x and with respect to y. What if x and y change together? Like x changes by some quantity 1, so x becomes x plus 1 and y becomes say y plus 2. Then what is the effect on fxy? So that is your concept of total derivative. So when we had a function of one variable, we didn't use this terminology total derivative. Because dy by dx, there we had only one variable. So dy by dx was the total derivative. It was representing the rate of change of y with respect to x. So we get this expression delta y by delta x is equal to. So we had this change in y divided by change in x is nothing but the rate of change of y with respect to x, which we were calling as delta y by delta x. Now, if we take this expression, we can also write change in y is rate of change of y with respect to x, and I can cross multiply this into change in x. So I can write delta y is nothing but dy by dx into delta x. So this expression can be used if you know dy by dx and you know the change in x, you can find out what is the change in y. So it is just another way of telling the same thing, that given a change in x, what is the change in y? You can find out by multiplying the change in x with dy by dx. So we will get the change in y. So this is the expression we get for a function of single variable. Now when z is a function of two variables, say z is f of x comma y. Now here I am telling that x changes by a small amount delta x and y is held fixed. Then now when I am talking about the change in z, it is like just the change in x, the same thing as we had for a single variable. So we have kept y as a constant. So delta z will be, only thing now here, dy by dx will be represented by the partial derivative of z with respect to x. Since I am changing x by a small amount delta x and looking at what is its effect on z. So I take del z by del x into delta x. So for a given small change in x, what is the change in z is given by this expression. Now similarly, for a given small change in y, that is delta y, what is the change in z? We can write it as, we take the rate of change of z with respect to y now. So we have del z by del y into delta of y, that will give me delta of z. So what is it? This expression represents the change in z because of a small change in x, and this represents the change in z because of a small change in y. Now if I want to find out the change in z with respect to a change in x and a change in y, both together, this we are looking at individually. Here y is kept fixed, here x is kept fixed. But now I say I am going to change both x and y, and tell me now how will z change. Then that is what is meant by a total derivative. So in practice, both x and y may change simultaneously. If this is the case, then what is the net change in z? This will be the sum of individual changes brought about by the changes in x and y separately. So the change in z is by x alone is, see, this expression. Because of a change in x, you have del z by del x into delta x. This is the change in z because of the change in x. This is the change in y in z because of the change in y. So we add these two expressions together, and this represents the total change in z when you have a change in x and you have a change in y. So this is represented as the small increments formula, or we call it as the total derivative of z. Okay. Now, when we have these infinitesimal values, that is, if we allow delta x to tend to 0 and delta y to tend to 0, as we did in the definition of our derivative, these deltas will be replaced by dz. So we will have the infinitesimal value. So when delta z tends to 0, we represent it as dz. So we get the expression change in z dz is nothing but the partial derivative of z with respect to x into the change in x, that is dx, plus the partial derivative of z with respect to y into the change in y, that is dy. So this is what is meant by a total derivative when you have z as a function of two variables. Now we can naturally extend it to a function of three variables. So for instance, we have a function w, which is a function of three variables, x, y and z. Now what is the total derivative of w? Just take the analogy from the previous slide. Instead of dz, I have d of w. So d of w. Then I will take the partial derivative of w with respect to x into change in x. So we have partial derivative of gx. So w is g of x, y, z. So I take the derivative of g with respect to x into d of x, plus partial derivative of g with respect to y into d of y, plus partial derivative of g with respect to z into d of z. So for an example, you can take this u, which is a function of t, r and s, and you can work it out now. What is ux? So the ut rather, we have the three variables as t, r and s. So we will have to find out u of t. When we do u of t, we will get, see, these two have to be treated as a constant. So t cube will just become 3t square. So we'll have 3t square r6 s square. These two will remain unchanged. So du will be 3t square r6 s square into dt, because now we are talking about the partial derivative of u with respect to t. In the next term, we will talk about the partial derivative of u with respect to r. So t cube and s square will remain constant. R6 will give me 6 r5. So this will be u of r into dr. And finally here you will have u of s into ds. So u of s will be, now here why we get a minus sign, you have to consider this as s to the power minus 2 and differentiate. So t cube r6 will remain as it is, and s to the power minus 2 will give minus 2 s to the power minus 2 minus 1, which is s cube. So work this out and see just with the power formula, d by ds of s to the power minus 2. When you evaluate that, you will get it as minus 2 by s cube. So this will be the total derivative of u, which is a function of three variables. Yeah, so we stop here. Next we will see the concept of directional derivative and the concept of gradient.